There was a comment earlier that a lot of the stuff in the first section doesn't show up, but it does. It's just you have to set up using stuff from the third section to get a problem from the first section. So a lot of these tend to be two problems in one. I'm not a huge fan of that just because it means if you set it up wrong, that means I have to figure out what you did for the second part and whether you did it correctly. So sometimes we tend to separate concepts a little bit more than this. But we'll see what we got. All right, so given the Maclaurin series for sine, find the Maclaurin series for sine of x squared minus x squared. Well, fair enough. All right, so sine of something looks like it's going to be sum of -1 to the k of the box to the 2k plus 1 over 2k plus 1 factorial, starting at 0. Okay, what are we going to put in this box? We're looking for the sine of x squared, right? So that's what goes in the box. All right, so let's see what we've got. K equals 0 to infinity, -1 to k. This is going to be x to the what? 4k plus 2, okay, over 2k plus 1 factorial. Okay, so let's take a look at our alternatives here. Now you got to figure we're going to have a 4k plus 2 somewhere. So 4k plus 1, that's not going to do it. 2k plus 1 is not going to do it. So we're down to whether we handle it this way or this way. So what's the difference here? Now we're supposed to subtract off x squared. Now this one's got a minus x squared on it, but you see when we're on this one, they're subtracting x squared from every term. Sorry. All right. Here, x squared is subtracted infinitely many times. That's probably not good. Now, how is it subtracted in that first one? Take a look at the difference between this and this. What's the only difference? Yeah. That one starts at 1, this one starts at 0, right? Now what's the first term of this?
Stupid doors. Yeah, he walks right in. I'm weak.
Here, tap this door.
Bless you.
Alright, so minus, this will be x to the 6th over times 1 factorial plus x to the 8th over, what, 5 factorial? Oh, is it 8 or is it 10? So it goes up by 4 every time, so it's 10. And so on. Alright, so if I subtract off x squared, what did I actually do? I just killed off the first term, right? So that's where we want D. We want this one because the difference between D and E is here the first term's just left off, so you killed off the x squared. Here you subtract off x squared for every possible term, so you subtract it off way too many times, right? See the difference? All right. So that one's D. So let's take a look at this. All right, which of the following are true? It's this kind of thing. At least they're not going haywire with the solutions, 1 and 2, 2 and 3, 1 and 3, etc. So, all right. Second degree Taylor polynomial at a equals 1. Okay. And I assume that's at the center at 1. So it should be what? f of 1 plus f prime of 1 times x minus 1. Right? That should be our second degree polynomial. Okay. Now, our third, so let's see. Which of the following are true? Now, this is about errors, right? So, R2 of x. Now, from Taylor's theorem, it's going to look like the third derivative evaluated somewhere divided by 3 factorial times x minus 1 cubed, right? Okay, so what's the third derivative of this function? So x to the 5th minus 1, f prime is 5x to the 4th, f double prime is 20x cubed, f triple prime is 60x squared, right? Okay. So this looks like 60 times something squared over 3 factorial times x minus 1 cubed. Now, where am I looking to evaluate my error? So I'm evaluating f of 0.9, right? So if I put in 0.9, what I've got here is 0.9 minus 1 to the third power. Okay, so I've got 60 times something squared over 6 times 1/10 to the third power. Okay, so let's see what we got. This is something squared. 60 and 6 are going to give you 10, and so I've got 100 on the bottom. Okay. And let's see. Now what I'm wondering at is why is there a negative? Oh, because 0.9 minus 1 is negative 1/10, right? Okay, so number 1 is definitely true, right? So for some c in between the place I'm evaluating the function and the center of my series. So this is definitely true. This is the error estimate from Taylor's theorem. Okay. Now we have to figure out whether or not 2 and 3 are true. All right, so let's reason our way through this. Suppose 3 is true. 2 is also going to be true, right? So you can't have just 1 and 3 without 2, just because if you're smaller than 0.008, then you're already smaller than 0.01, right? So that doesn't make any sense. All right. It's not 2 only, and it's not 3 only, because we know 1 is true. So, all right, it's either going to be 1 only, or it's going to be 1 and 2. So, what do we know about this guy?
fx to the 4th.
Yeah, well, we know it's, whatever this place I'm evaluating it is between 0.9 and 1, right? Okay, so where is the largest value of this guy going to happen, of the absolute value? It's going to happen at 1, right? And so this says that the absolute value of R2 of 0.9 is definitely going to be less than 1 squared over 100, which is your 0.01, and that happens to be statement 2. So this is true because c squared over 100 is less than or equal to 1 over 100 when c is between 0.9 and 1. Does that make sense? So again, that's coming out of the, this is the actual estimate from Taylor's theorem, and this is coming out of that upper bound where your capital M ends up being 1, just because the place you're evaluating, because it's one of those things out of mean value theorem, and it comes from the upper bound on that. So it looks like 1 and 2 only are going to be what you want for that. All right. So again, you notice a multiple choice question, we could weed out some of the choices just because they didn't make any sense, right? So look for that kind of thing. You can always narrow it down to a couple of choices. That's what you want. Okay. area of the region bounded by r equals square root of 2 cosine of 2 theta. So we've got some kind of a polar function. Now, do I know what it looks like? Not really, but you figure this has got some kind of loops, right? All right, so how do I find a loop? I'm going to set square root of 2 cosine of 2 theta equal to 0, and I'm going to look for 2 consecutive places where that's equal to 0. Okay, so let's see. That means cosine of 2 theta is equal to 0. Okay, so where's cosine equal to 0? Yeah, here and here, right? So that means 2 theta is either going to be pi over 2, 3 pi over 2, and let's look at it for theta all the way from 0 to 2 pi, just to see what kind of things we're looking at. Okay, it could be, and that's it, right? So that would mean theta is pi over 4 and 3 pi over 4. Now the thing that bugs me about this is, if I'm looking for theta between 0 and 2 pi, do I need to look at 2 theta between 0 and 4 pi? Because I'm going to end up dividing these angles by a half. So let me, or dividing by 2. So also 5 pi over 2 and 7 pi over 2. Let me throw those in there, just so I'm looking at 5 pi over 4 and 7 pi over 4. Because if you look at the behavior of cosine of 2 theta, what does it look like? Just the rectangular one. In between 0 and 2 pi, it's going to do this thing twice, right? Okay, so where are your loops going to come from? If I'm taking the square root of this function, what's going to get thrown out? That part and that part, right? I never touched that, but in between, what is this, 3 pi over 4 and 5 pi over 4, that's going to give me a loop, right? And in between negative pi over 4 and positive pi over 4, that's going to give me a loop, right? So, and let's see. Is that right? Yeah. Okay. So, what I suspect is going to happen here, so here's negative pi over 4, here's positive pi over 4, and I've got one loop that comes out like that. Now, in between 3 pi over 4 and 5 pi over 4, I'm also going to have a positive loop that's going to come out like that. So I think what I'm going to get is like this figure 8 kind of a shape here, is what this is. So, if I want the complete region bounded by this, I've got 2 pieces, right? So I would say, let's find the area of this guy and multiply it by 2. I don't know if both choices are going to be on there, but let's be careful that we get both of them. So, alright. So, I know area is the integral of 1/2 r squared d theta. I'm going to multiply that by 2, and then integrate from negative pi over 4 to pi over 4. Again, that's just the fact that that creature over there has got 2 eyes, right? I have to get the area of both of them. Now 2.5 are going to cancel out. So I've got the integral from negative pi over 4 to pi over 4 of what? When I square root 2 cosine of 2 theta, I just have 2 cosine of 2 theta. So that should be easy enough to integrate. Okay. This is going to be, when I integrate cosine, I get what? Sine and divide by 2. So it's going to be sine of 2 theta, evaluated at negative pi over 4 to pi over 4.
Do you have to use the double angle identity for that?
We don't. Just because when you're integrating cosine of 2 theta, you can just divide by 2. If you did that as cosine squared minus sine squared, you would probably have to then go back, use half angle formulas, and arrive back at this thing again. That sort of thing. So it's only when you have squares or powers of trig functions that you have to do something to mess with them. If it was cosine of 5 theta, you just divide by 5. All right, so I've got sine of 2 theta evaluated at these 2 points. So I've got sine of pi over 2 minus sine of negative pi over 2, which I believe is 1 minus negative 1. So it ends up being 2. Oh man, and they're devilish this time because 1 and 2 are both answers, right? So this is the area of one side, and so 2 is the area that we actually want. That's tricky.
What happened to your 2 inside the integral?
Just because when you integrate cosine of 2 theta, you're going to have to divide by 2. So they cancel out. So that's a devilish problem there. That's tricky. All right. Well, we can still get through it. Just have to take your time and see what it is that you're looking at. All right, radius of convergence of the power series. So, ratio test, right? Now, what's your gut feeling here? I got an x to the n on top, and I got an n factorial on the bottom. What does it look like anyway? If I factor out the 2, I've just got x to the n over n factorial. That's a series for e to the x, right? Where does that converge?
1.
Everywhere. Right? So it's probably going to be infinity. But let's double check. If I say an is x to the n over 2 times n factorial, and an plus 1 is x to the n plus 1, 2 times n plus 1 factorial. Alright, so the limit as n goes to infinity of an plus 1 over an an absolute value is the limit as n goes to infinity of absolute x to the n plus 1 over x to the n times n factorial over n plus 1 factorial, which is the limit as n goes to infinity of absolute x over n plus 1, right? Because your n factorial and your n plus 1 factorial just leave an extra n plus first term on the bottom. So what does this do as x or as n goes to infinity? Goes to 0, right? Because x is fixed, right? So for any fixed value of x, for big values of x, it's going to take a while, but for any value of x, it's going to go to 0. So 0 is always less than 1. This converges for all x, right? So your radius of convergence is going to be infinite on that. Okay, which of the following represents a solid so what do my graphs look like? I've got cube root of x, and I've got x squared, and I'm going around the x-axis. So I've got kind of like a tulip, right? That I'm looking at here. Now, looking at these, does it look like they're doing shells or washers? Looks like washers, right? Because I got a radius or something squared minus something squared. So here y is x to the 1/3, and here y is x squared. So my volume one way is the integral from 0 to 1. Yeah, because that's 0, 0, and that's 1, 1. Of pi times my outside radius squared, which will be x to the 2/3. Minus my inside radius squared, which is x to the 4th. All right, how does that show up?
Yeah, D. I just factored out a.
What do you think about this?
No.
2/3, and then that's 3/2. No.
What's the formula for the walking method again?
It's outside radius squared minus inside radius squared. None of these look right. Okay. Do you want to see if maybe they did it by shells? Because there's also some that are dy. So if I did shells, well, y is cube root of x means that x is y cubed. And here, y is x squared means that x is the square root of y. Okay. And so that would mean that my volume would be 2 pi times, I need a radius and a height, right? Alright, so what's my radius if I'm breaking it up this way? It's just y, right? Okay, and what's my height? That would be top function, which is y to the 1/2, minus bottom function, which is y cubed. Alright, so what I've got is 2 pi, integral from 0 to 1 of y to the 3/2 minus y to the 4th, which actually is a choice, right? So this is tricky because you got two different methods that you can calculate this volume. And one of them's on there, but it's not the one that I thought it was going to be, right? Because I was thinking it was going to be washers because all of these are differences. But by shell method, it actually gives you C. So only one of those works, but you had them in both methods. Alright. Arc length of the graph.
I did have a quick question.
Yeah.
On the final, are we still one note card or are we allowed to use two?
I believe it's one, but I'll double check.
That'd be great if it's 2.
Let me see.